there are different things that I can do to check that all the variables have been calculated with proper delays. Let's say if I go back to the data and I say, well, actually, I do not have a delay for this particular value. I'll just put it to 0. I go back to the main. I do not have to reset the Jacobian because I can reuse the same structure. In any case, I can rerun. It has started from the user, but I could also restart the initial guess from the solution. It would go even faster. And then I can go to the plot, see again the insertion indices, and I see that this time, well, I do still have a delay for the lower arm modulation indices, but I do not have a delay for the upper arm insertion indices, which is indeed what I had requested with this line. And I can also, for instance, put, let's say, what if the lower arm insertion index has twice the delay of the upper arm? Naturally, I do not know of practical examples where this would be the case, but this toolbox gives you the flexibility to do such calculations. So let's start again running the collocation method, check the plot, control enter, and we see that this time the delay related to the upper arm is twice as small as the delay of the lower arm, which is indeed what we have requested. Excellent. So as before, we don't only have the collocation method, but also the time domain simulation methods. So what I have to say here is that it doesn't matter which solver you request. If you are working with a delayed system, it will automatically be DDE23. This is the Matlab solver that will be automatically used with delayed systems. For my PhD thesis, I have also implemented ways of solving delayed systems with solvers dedicated to ordinary differential equations. However, I have only written those files for specific cases. I have not generalized the approach, hence it is not made available as part of this toolbox. But in any case, you can do those time domain simulations of delayed systems with DDE23. So let's see, we'll keep the same sampling period, which is the time step. We'll solve for five fundamental periods, and we will start from the source, this particular source. So the steady state calculation that we have done with the collocation method describes a periodic trajectory, and we say that the time domain simulation should start on the periodic trajectory. Naturally, it is a delay. It is a delayed system, so it also needs history values. Those history values are also part of the periodic trajectory, so they are easily calculated, and this is automatically done by the toolbox. So I can run this one. You see that unlike the solving of ordinary differential equations, solving this system starts automatically with DDE23 as solver, but also that the presentation is different. For delayed systems, the complete time span is split into subintervals. Actually, each subinterval has the length equal to the smallest delay. And also you see that it is taking much longer. So it is much more computationally intensive to solve for a delayed system with Matlab. Please be aware that there are other ways of solving delayed differential equations. This is only one particular option. Okay, so the extraction of the signals is done. See that I have also the usual Fourier analysis of the last fundamental period and of the last XP fundamental periods still equal to 3 in this particular case. I can go and check the results. This time not the collocation method, but the complete time span that has been solved by a time domain simulation. Here is what it looks like. There is indeed still a small difference between upper arm and lower arm. This is the result of a small transient, and still I see that indeed the code has accounted for the delays. We still have this smaller delay for the upper arm and larger delay for the lower arm. So this is the solution of a delay differential equation. This time, if I would like to add one more, well, to extend with additional results, I would like to solve for one more fundamental period. I can start from the solution. This will not work. And the reason is that when you are considering delayed systems, if you start from the solution, you have to start from the last time value. So we have solved up to this particular time value. And now I would like to have one more fundamental period. Well, I can do it like that. 1 time 0.02. Alternatively, and even more simply, I could do this like that. And then I start again the calculation. So naturally this time we are solving for only one fundamental period. However, we are requesting Fourier analysis on the last 3 fundamental periods. This is naturally not possible. So the code will automatically reduce XP to 1. We will see this once the numerical integration has stopped. So the reason why this is slower is also because we have 2 different delay variables. If you have only the same delay value for both insertion indices or for all insertion indices, well, the calculation goes also faster. The more delay values you have, and more specifically, the more different delay values you have, the slower the integration of the delayed system. So in any case, if we go to DSA time domain simulation options, we see that XP has been automatically reduced to 1 fundamental period because the time span covers only 1 fundamental period. If we had asked for even less than 1 fundamental period, the toolbox would have said that there is not enough points, that the time span is too short to do any Fourier analysis. Naturally, you could bypass that by improving the code. We can have a look at the results once more. Naturally, this time the complete time span starts from 0.1 second and covers 1 fundamental period. So this is, I think, everything that I had to say about time domain simulations of delayed systems.